the greatest common divisor. Of two numbers is the largest number that divides both of them evenly. Computing it is one of the oldest algorithms we have, written down by Euclid more than 2,000 years ago. Let us watch it run on 48 and 18. Divide the larger number by the smaller one and keep only the remainder. 48 is 2 times 18 plus 12. Now repeat with 18 and 12. 18 is 1 times 12 plus 6. Repeat once more with 12 and 6. 12 is exactly 2 times 6, with remainder 0. The instant the remainder reaches 0, the last non-zero remainder, 6, is the greatest common divisor. Look closely at what the algorithm actually does. It holds a pair of numbers, a and b, and it replaces that pair with b and the remainder of a divided by b. Then it does the same thing again, nothing else. It never factors the numbers, it never consults a table. The only operation it ever needs is division with a remainder.
How do you know it does not just run forever?
Because each remainder is strictly smaller than the one before it. The process cannot run forever. It must reach 0 and it must stop.
Can you actually divide one polynomial by another and get a remainder, the same way you divide whole numbers?
Yes, and it is nothing exotic. It is just the long division you learned in school, carried out on terms instead of digits. Let us divide x to the fourth plus 1 by x squared plus 1. The leading term, x to the fourth divided by x squared, gives x squared. Multiply back, x squared times the sum of x squared, and 1 is x to the fourth plus x squared. Subtract, and the x to the fourth cancels, leaving negative x squared plus 1. Divide again, negative x squared over x squared gives negative 1. Multiply back, negative 1 times the sum of x squared, and 1 is negative x squared minus 1. Subtract, and what remains is just 2. We stop here because the remainder 2 has degree 0, which is smaller than the degree of the divisor, x squared plus 1. So x to the fourth plus 1 equals x squared plus 1, times the quotient x squared minus 1, plus the remainder 2. That is exactly the shape of integer division. The dividend a equals the divisor b times the quotient q, plus the remainder r, with the remainder strictly smaller than the divisor. For numbers, we measure that size by magnitude. For polynomials, we measure it by degree. Step back from the particular numbers and polynomials and ask what the algorithm really required. Just 2 things. First, a setting where you can add, subtract, and multiply, what algebraists call a ring. Second, a way to divide with a remainder that is always smaller than the thing you divided by, where smaller is measured by a size function called a norm. A ring that carries that kind of division has a name. It is a Euclidean domain.
Hold on, integers and polynomials satisfy that same requirement.
Line for line. Integers and polynomials are both Euclidean domains, and they line up property for property. The norm of an integer is its absolute value. The norm of a polynomial is its degree. Integer division gives you an equation. The dividend a equals the divisor b times the quotient q, plus the remainder r, with the absolute value of r smaller than the absolute value of b. Polynomial division gives the very same equation, with the degree of r smaller than the degree of b. And the greatest common divisor. For integers, the greatest common divisor of 48 and 18 is 6. For polynomials, the greatest common divisor of x squared minus 1 and x minus 1 is x minus 1. The norm strictly decreases at every step, and that single property is what makes everything work. Each remainder is smaller than the last, so the sequence of remainders cannot keep going down forever. It has to reach 0, and the algorithm has to terminate. That guarantee is not a fact about integers, and it is not a fact about polynomials. It is a fact about Euclidean domains, and both of them happen to be 1.
Wait, the exact same code, unedited, on 2 totally different kinds of values.
Watch, here is the greatest common divisor algorithm, written once, generically, While b is not 0, replace the pair a, b with b and a modulo b. And when b finally reaches 0, return a itself. The type of a and b is left abstract. Any Euclidean domain will do. We are going to run this single piece of code in 2 different worlds at the same time, and never change a line of it. On the left, a and b are integers, 48 and 18. 48 modulo 18 is 12. 18 modulo 12 is 6. 12 modulo 6 is 0. The loop ends, and the answer it returns is 6. On the right, a and b are polynomials, x cubed minus 1 and x squared minus 1. X cubed minus 1 is x times the difference of x squared and 1 plus x minus 1, so the remainder is x minus 1. Then x squared minus 1 is x plus 1 times x minus 1 with remainder 0. The loop ends, and the answer it returns is x minus 1. 2 traces side by side. The numbers shrink by magnitude, the polynomials shrink by degree. But the algorithm is identical, character for character. We did not write a special polynomial version of greatest common divisor. We wrote one greatest common divisor and handed it a different structure. Same algorithm, swapped structure.
One greatest common divisor, and it just works on both.
Recognizing the structure does more than hand you one algorithm. It hands you a whole family of them. The extended Euclidean algorithm runs the very same loop while tracking a little extra bookkeeping, and out falls Bezout's identity. The greatest common divisor of a and b can always be written as a times some polynomial s, plus b times another polynomial t. The proof for integers and the proof for polynomials are, line for line, the same proof. Here is a gift that feels almost magical. Take a polynomial with a repeated root, say x minus 1 all squared, which expands to x squared minus 2x plus 1. Its derivative is 2x minus 2, that is 2 times x minus 1.
How would dividing by a derivative ever find a repeated root?
Just compute the greatest common divisor of the polynomial and its derivative. It comes back as x minus 1, exactly the root that was repeated. The Euclidean algorithm, with no notion whatsoever of calculus, just located the part of the polynomial that repeats.
So all of that comes free with no new proof at all.
All of it, once you know a structure is a Euclidean domain, you inherit, already proven, the greatest common divisor. Bezout's identity. The least common multiple. Unique factorization. Into irreducibles, and the Chinese remainder theorem. You do not reprove a single one of them. They are consequences of the structure, and the structure is all you ever had to check. This is Stepanov's thesis in a single example. Greatest common divisor is not really an operation on integers. It is an operation on Euclidean domains. And the integers are just one example of one. The same is true of polynomials over a field. When 2 things share a structure, they share its algorithms.
So the greatest common divisor was never really about numbers at all.
So you write the algorithm once against the structure itself. Constrain the type to be a Euclidean domain, and the body is the same 3 lines Euclid would recognize. Then integers work, polynomials over a field work, the Gaussian integers work, and anything you meet tomorrow that turns out to be a Euclidean domain works too, with no new code at all.
So where do you actually start, if not with the concrete numbers?
That is the lesson, and it runs backward from the way we usually program. We tend to start from a concrete type and write an algorithm for it. Stepanov asks us to start from the structure and let the algorithm follow. See the structure first.